Think about it. Okay, so good morning, everyone. Today you have the pleasure of hosting Professor Flaminia, and she'll talk about quantum reference frames. Professor, thank you very much for accepting the invitation, and you may start whenever you're ready.
Thank you very much for the introduction, and thank you for the nice invitation to present my work here. So this will be some very broad perspective on some research that I've been working on in the past few years that is around the topic of quantum reference frames. And I will explain I will introduce this concept and I will explain the basics. And then I will argue that this is a useful tool if we want to talk about non-classical space-time. So we have in physics, we have our two main theories. There are two most fundamental theories that are general relativity and quantum theory, and they both rest on the classical notion of space-time. So in both of them, space-time is classical, but we know that if we want to combine them into a quantum theory of gravity, then space-time should acquire quantum properties. And however, we do not know what will replace this classical notion of space-time at the interface between quantum theory and gravity. So this question has been addressed in quantum gravity, typically in the high energy regime, where, however, it is very hard to find some observational implications. So today, I'm going to take a different perspective on this topic, which focuses in the low energy regime, where gravity is perturbative and we can meaningfully talk about quantum particles. So I will focus on some specific examples, which, however, bring out some fundamental questions that arise also in more traditional quantum gravity scenarios. And the advantage of doing that is that here we can talk about concrete physical situations which have an immediate counterpart in terms of laboratory operation. So it is an operational approach. And so just to frame the general context, let us consider the fundamental equations of general relativity, the Einstein's equations. So here we have that on the right-hand side, we have matter, and on the left-hand side, we have gravity. And these equations are defined when the stress energy tensor that describes the matter configuration is classical. However, in quantum theory, we know that matter is ultimately quantum. And hence, we would like to replace this classical stress energy tensor with a quantum operator. However, if we do that, this equation doesn't make sense anymore. And then we can ask, which type of structure replaces it, and how do we address this? So an easier way of doing it is to consider a regime in which we can linearize these equations. So basically, we treat the gravitational field as a background that we can take, for instance, as Minkowski, on top of which we have some quantum perturbation, and we quantize this perturbation. And then we could be tricked into thinking that this is actually not a non-classical space-time, because we can always refer to a background. However, if we put a clock, for instance, here, then this clock will feel a different gravitational field, whether the mass is here or here. And this is the type of situations that we can describe. And so the typical situation we will be concerned with is when we have a quantum source of the gravitational field that is prepared in a quantum superposition of two locations. And another interesting aspect of considering this situation is that experiments are on their way towards realizing this in the lab. And in particular, there are two different directions in which experiments are focusing their efforts. And these are, on the left-hand side, experiments that try to measure the gravitational field of some classical objects and try to reduce as much as possible the mass of the object that sources the gravitational field. And currently, the state of the art is in Markus Permayer's lab in Vienna, where they have the lightest gravity source that is 90 milligram. And if you look at this, this is much smaller than a coin, this source of gravity. And on the other hand, there are other experiments that try to push quantum properties at more and more macroscopic regimes. So for instance, they try to increase the range of masses that can be put in a quantum superposition state, or they try to increase the size of the quantum superposition. And these are two examples of some recent experiments that are like state-of-the-art experiments. And of course, in the end, the goal is to bridge these two regimes. So to measure the gravitational field of a quantum object that is in a quantum superposition state. And this is clearly a very complicated target to achieve. And it's mainly limited by decoherence effects, like scattering black body radiation. And in this paper by Markus Aspelmayer from last year, you can find a very good review of what the current status of experiments is and where the difficulty lies. So why is this interesting? This is not quantum gravity. This is a different regime, and these are, we think about this with different tools. So why is this interesting? So here I listed some motivation. This is my personal motivation. If you ask somebody else, it will be, they will give a different answer. And I have three different reasons, and these are ranked from the most conservative to the most speculative one. So the first one is that we have scarce evidence for quantum gravity, and we also do not know, there is no agreement in the community about which type of observation we would need to show that gravity is not has quantum features. And we also do not know how far we can test it with tabletop experiments, such as those that I had in the previous slide. But we also know that experiments are trying to make their way towards realizing this situation. And so it is very interesting for us as theorists to see how far we can go with this approach. The second reason is that there are some open questions in quantum gravity that also show up in this regime. And what I'm thinking about is, for instance, the lack of a classical spacetime, quantum time, causality, or how to identify observables, the fact that the Hilbert space has a different partition into local subalgebra or subsystems. And these are all questions on which we can make conceptual progress already in this regime. Hence, this can give us an indication of what will happen then. So it will help us to build intuition to then proceed to higher energy scales. And finally, the most speculative reason is that this is some research that imports quantum information tools and applies them to the question of putting together general relativity and quantum theory. So if we think about the device-independent reasoning that we learned from Bell's theorem, then we know that this is not tied to a specific regime, but on some probabilities that we can measure in an experiment and on some very general principles. So the hope is that using these internal consistency arguments, then we can understand which one of our assumption will fail, and hence this will give us indications of how to proceed further away from the scales that we can currently look at nowadays, or with this type of experiments. Now, after the introduction, I would like to introduce you to the topic of quantum reference frames. And first, I will use some very general definitions, and then I will tell you how this is related with what I've been talking about so far in the introduction to the general topic. So, what is a reference frame? In physics, we can think of a reference frame as a set of axes that we use to describe physical systems. And reference frames are a very useful concept because they allow us to fix the point of view from which observations are made. But we also know that we can choose whatever reference frame we like, and we can still talk about the laws of physics. We can still formulate the laws of physics in arbitrary reference frames. And now let us consider just non-relativistic quantum theory. So just the quantum mechanics as we learn it in third year courses at university. And let us imagine now that we want to change the reference frame from some initial one to another one that can, for instance, be translated or moving at some relative velocity from the point of view of the first one. In quantum mechanics, this is encoded in a unitary operation where what I would like you to focus your attention on here is that these x0 and v are the relational parameters. So basically, it's the relation between the initial and the final reference frame. For instance, the relative distance between the two origins or the relative velocity between the two frames. And these quantities enter the transformation as a parameter. So they're not dynamical variables. They are not operators. They're just a parameter. And if we have a Schrödinger equation, a theory that obeys the Schrödinger equation initially, then after a reference frame transformation, we still have a Schrödinger equation, provided that we changed our Hamiltonian according to this law. And this encodes the covariance of physical laws in quantum mechanics. This rule here. In addition, we speak about a symmetry of the dynamical law if the functional form of the Hamiltonian after the transformation is the same as the functional form of the Hamiltonian before the transformation. But now, let us imagine that we have this situation with three particles, A, B, and C. So a first element that we want to consider is a relational approach. This means that if we have these three particles, the center of mass degree of freedom is not something that we can observe. And the only thing that is physical are relational quantities between A and B, A and C. So in this example that I drew here, the only variables that make sense from the perspective of C is the relative position between A and C and the relative position between B and C. And in the same way, the relational variables, a set of independent relational variables from the perspective of A is the relative position between C and A and between B and A. And then, of course, I can talk about also this one, but I have just two positions, two systems that I'm describing. So this means that if I stand in C, I am not describing C with respect to itself. I'm just describing these two particles here. And if I stand in A, I'm only describing these two particles here. So the number of degrees of freedom is the same, but I reshuffle the information when I change the reference frame. And this is still classical. Now, let's add some other elements. So whenever we make an observation, we always take as reference a physical system. So for instance, if I want to measure a distance, I take a ruler, I put it on some physical system that is the origin, and I count how many ticks of the ruler are until the object that I want to measure. And I also use physical objects. I use a ruler that is actually a physical system. But we also know that physical systems are ultimately quantum systems. So the question that we want to ask is, imagine now that these rocks have a quantum state. So they can be in a quantum superposition or even entangled with other physical systems. Does it make sense to just put a coordinate system on top of this quantum system? Can I attach a quantum reference frame to an object whose state is in a quantum superposition state? And in particular, to be a bit more precise in the way we will formulate this question, we want to start from the perspective of some reference frame, quantum reference frame C, that describes A and B, and then move to the perspective of a quantum reference frame that is centered on the position of a quantum system A. And from this quantum reference frame, we describe the state of B and C. That is a quantum state. Yes, I see a question.
Oh, hi. It's been, first of all, thank you for giving me the talk for us here. I just have a question because when I build reference systems on classical mechanics, or even general relativity, what you have is the space-time, and then we put labels on every event in space-time. This is basically a coordinate system. I cannot understand how can we univocally put labels in each event of the space-time when we are doing certain things like this. I mean, quantum reference frames. I don't understand the meaning of coordinates. That's my question, actually.
What the meaning of the coordinates? Okay, so maybe it will become clearer when I actually explain what a quantum reference frame is.
Okay.
But basically the idea is that, so imagine that, so you are in your lab and you see a quantum system, and then you want to apply a quantum superposition of reference frame transformations to go to the frame that is centered on this quantum system. So basically the meaning of the coordinate system is the same as in standard physics, like in standard physics. It's just that you put it in a quantum superposition.
Okay, I can do this. But before doing this, I needed to set up coordinates, classical coordinates in the entire space-time. And then I cannot talk about quantum gravity effects or anything like this, because gravity is a classical thing in the end. Or am I missing something here?
So at this level, we haven't included gravity yet. And what we're doing for gravity is still at the very beginning. However, so this is not going to talk about full quantum gravity. I'm not asking this question.
Okay, yeah.
And so we only want to talk about a regime in which it makes sense to associate, to have a superposition of spacetimes. I will give an example later. So maybe we can discuss it after.
Okay, maybe to become clear. Okay, thank you.
Yeah. Okay, so let us consider the simplest case, that is a spatial translation in one dimension. So here we want to go to the relative coordinates between, so we start from C, but then we want to describe everything relative to A, in relative coordinates to A. And again, this is just the standard Galilean quantum mechanics, so it's nothing complicated. Then, imagine that now we have a quantum system A that is well localized in X1. So now we know how to move to the frame that is centered on A. We just apply a standard translation by X1. And so what we will do, we will move the origin to A, and then we describe C as being in minus X1 and B as being in X0 minus X1. And in addition, we have this operator that ensures that this state here becomes this state here. So basically that if C sees A in X1, A sees C in minus X1. So that's the only meaning of this operator. But now, let us imagine that instead of having this sharply defined position, we have a quantum superposition of two positions. So clearly now there is no single position by which I can translate to go to the quantum reference frame associated to the position of A. So what can we do? A possibility is to take seriously the linearity of quantum theory and say, okay, I cannot just translate by one single position, but I can translate in a quantum superposition. So in quantum information terms, I can apply a quantum controlled translation on the system, where B is the target system and A is the control system. So in other words, if you see here, what before was a parameter of the transformation becomes an operator that acts on the Hilbert space of the quantum reference frame. What do I obtain? So basically, I obtain this situation, which I can understand as when A is in X1, then this becomes X1, and I translate B and C by X1. So A is here at the origin, and B is in X0 minus X1, and C is in minus X1. When A is in X2, XA becomes X2, and then I translate B by X2, and C becomes minus X2. So the first thing that you can see is that here I had a product state, and here I have an entangled state. This is not surprising because this is an entangling operation. It mixes two Hilbert spaces. So in the end, what I get is that entanglement and superposition are quantum reference frame dependent features. So they're not something that is fixed a priori, but they depend on my choice of the quantum reference frame. In other words, this means the quantum reference frame transformation changes the partition of the Hilbert space. So the one I presented is the simplest transformation that you can imagine. There are more complicated ones where we can also do, say, superposition of translations, superpositions of boosts. But all of them, all those that I found so far have this structure, where this one is a standard reference frame transformation. So it can be translation boost, the transformation to an accelerated frame, a Lorentz boost, and so on. And this one here is a control parameter. So basically, the parameter of the transformation is controlled on an additional Hilbert space that is the Hilbert space of the quantum reference frame. So we can think of this, for instance, as being the position or the velocity of the quantum reference frame. Now, so far, I have not included any dynamics, but of course, we should have also some dynamics. So let us consider just without quantum reference frames, just standard transformations of reference frame in quantum mechanics. So if we have the Schrödinger equation, we have a Hamiltonian. And as I mentioned at the beginning, when we apply a unitary transformation, potentially time-dependent, then we still have a Schrödinger equation if we change the Hamiltonian in this, according to this law. Now, if we have that the parameter of the transformation is of this type, so it's either x0 or v0t, then if I start from the free particle Hamiltonian, when I change the reference frame, I still get a free particle Hamiltonian. So basically, if I just perform a translation or a boost, a free particle is still a free particle. I'm not saying anything more. Now, what happens in quantum reference frames? So first of all, as I mentioned, the parameter, so the general recipe for a quantum reference frame transformation is I take the parameter, I promote it to an operator on the Hilbert space of the quantum reference frame. So in this case, x0 goes to the position of the quantum reference frame, and v0 goes to PA divided by MA of the quantum reference frame. And then when I consider my Hamiltonian, I don't have only the Hamiltonian of the system that I'm transforming, I also have the Hamiltonian of the quantum reference frame. So in this case, I want to start from a free particle Hamiltonian with two particles, A and B. And then I move to A. And I will not show the explicit form because it's a little bit complicated, but you can have a quantum reference frame transformation such that this free particle Hamiltonian is mapped into another free particle Hamiltonian, where you see all labels A are swapped to labels C. So this is our definition of an extended symmetry transformation under a quantum reference frame transformation. Okay, so this is a good moment to stop if there are questions.
Oh, I actually have. I think I didn't understand it precisely what you just did. I mean, for me, is an exchange of particles.
Sorry, what do you mean? Which one?
The transformation that you just did in the last slide.
This one.
Yeah, that one, the last one.
Mm-hmm.
Why is this different from just swapping the particles?
So, okay. So basically what we're doing here is, okay, so this is a concept that is a bit hard. So intuitively, whenever we write a quantity, so x, b, say, this is not the position of a particle. This is the relational information between two particles. So if I stand in C, this is the relational position between B and the origin of my reference frame. So it is not a property of the particle, it is a property of the relation between the particle and the reference frame. This means that when I move, I change to a different quantum reference frame, I can still write PA and PB, but this is PA and PB from C or PA and PB from A. So I don't want to overload the notation, but the more precise notation would be PA from C and PC from A. So it's basically the same type of information, but it's just reshuffled around.
Okay. 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 I think I got it much. Okay.
Okay.
Thank you. Thank you.
Okay. Okay. So now I promise that there will be some connection with gravity. So here it comes. So I'm going to talk about two different things. The first one is a more speculative and fundamental, so at the conceptual level. And the second one is instead an experiment that we can actually do. So this first topic is the Einstein equivalence principle. So the statement of the Einstein equivalence principle that we consider is that if we have a gravitational field, then we can find a diffeomorphism transformation to any point such that locally the metric is Minkowski at that point and its first derivative is 0. So now let's take this statement for granted in just classical space-time. What happens now if we have either a particle that is delocalized in a quantum superposition of two positions or a superposition of classical gravitational fields? So what we came up with is that we can generalize the Einstein equivalence principle to both these situations. And I will not enter into details because it would take a whole other talk. I just wanted to tell you how this is related to quantum reference frames. So now in this first situation, imagine that we have this particle that is in a quantum superposition in the gravitational field of the Earth. And now we want to find a quantum reference frame transformation to the position of this particle such that at the location of the particle, we can make the metric locally Minkowski. And its first derivative vanish. And so we can build such a transformation. And in particular, with that, then you can also come up with a test with atom interferometry of this type of situation. So basically, it is a test with entangled clocks that are sent in a quantum superposition in this interferometer. And we find that if this generalization of the Einstein equivalence principle is not valid, it is not even possible to define time evolution in a quantum reference frame. So we lose the meaning of what it means for these clocks to tick. in this quantum superposition. Now, if instead of having a classical spacetime, now we consider a quantum superposition of, say, a massive particle in a quantum superposition state, and then we imagine a particle that is a test particle that is entangled with this mass in a quantum superposition state, we can still play the same game and find the transformation such that at the location of this particle, the metric is locally Minkowski. And in this case, we applied this in this paper to Penrose spontaneous state reduction. So, okay, so to give you some context, Roger Penrose considered a mass in a quantum superposition, and he argued. So there are many. He argued in many different ways, but in a version of this argument, he says that this massive quantum superposition cannot be a stable configuration, but it has to lead to spontaneous state reduction because of a fundamental clash between two principles. One is the principle of linear superposition, and the other one is the Einstein equivalence principle. And then, because of this clash, then he argues that one of them has to be abandoned. And he wants to put general relativity first, so he abandons the principle of linear superposition. And what we're saying here is that it is not necessary to abandon one of them. We can keep both of them as long as you're ready to generalize them to this more general configuration and to quantum reference frames. Now, let us step back a little bit. And now I want to consider a more concrete scenario that is really related to the experiments that I mentioned at the beginning of my talk. Let us take a massive particle, let us put it in a quantum superposition in the lab. And this is an old question. It at least dates back to 1957, when Richard Feynman at the Chapel Hill Conference proposed a thought experiment that involved a mass in a quantum superposition and concluded that if you believe in quantum mechanics up to any level, then you have to believe in gravitational quantization in order to describe this experiment. However, Feynman had something very precise in mind with this. The only thing that he meant is that the state of the gravitational field is in a quantum superposition. So he was not talking about gravitons, he was not talking about quantum theory of gravity, just the state of the gravitational field is in a quantum superposition. Then many people followed up on Feynman's thought experiment, and there was a lot of literature arguing in favor or against the quantization of gravity. I don't have time to review this literature, so let me just flash forward to 2017, where there were two papers that came out on the archive on the same day that proposed a variation of Feynman's initial thought experiment that involves two masses that are initially prepared in a product state in a quantum superposition. And then they are a source of a gravitational field, and they interact via the Newtonian interaction. So after some time, you will find that they are in an entangled state, and you can test that it is an entangled state. And then they applied a fundamental theorem in quantum information, stating that local operations and classical communication cannot generate entanglement. And they concluded that if entanglement is detected, then gravity cannot be classical. There were many reactions to this thought experiment, and that went into two completely different directions. On the one hand, people were arguing that these experiments cannot conclude anything about the gravitational field because it's just a Newton potential, which is just what remains of the gauge freedom of gravity. So you're actually testing the quantumness of matter and not of gravity. On the other hand of the scale, there are instead people who think that this actually really can test graviton effects. So I think that both these views are a bit too extreme, but I still think that there is something very interesting that can be tested here. also at the conceptual level. And it depends, so how far you can test also depends on how much assumptions you want to put in. But there have been many interesting arguments that have been put forward related to the locality of the interaction, the fact that the Newton potential is actually frame dependent, that the gauge split is not physical, and that you have the possibility of making arguments that test the theory from a theory-independent perspective. So in a framework that goes beyond quantum theory. So this is just to motivate the recent interest in these tabletop experiments that put a mass in a quantum superposition. I want to add one more layer to that, which is the superposition of gravitational fields a relative concept? So with quantum reference frames, just in the Newtonian, like in the Galilean limit, we have seen that entanglement and superposition, and hence also the localization of a quantum system, is not something that we can define a priori, but depends on the specific quantum reference frame that I pick. Is this true also for the gravitational field? And if this is true, up to which level it is true? And to do that, we asked this question in a very concrete experimental setup that is an atom interferometer. And this is in particular an experiment that was performed last year in the group of Markasevich at Stanford. And this is an amazing experiment. So let me just describe it briefly. So what they have here is an atom interferometer, atomic fountain. So you have to imagine a cylinder that is 10 meters high. And at the bottom, you have a source of atoms that is sent up in the gravitational field. And then it is split into different paths, which are, let's focus on the red particle, these two red particles here. At the highest point of the interferometer, the distance between this quantum superposition is 25 centimeters. And then they fall down and they are recombined, and you measure the interference pattern at the bottom of the interferometer. In addition to that, what they did was to put this half donut, which is a tungsten mass, which weighs 1 kilo. So the scheme in a freely falling frame, we can actually even simplify it more, because this particle is there for experimental purposes, but as theorists, we only care about this picture, where this is in a freely falling frame. So this is the tungsten mass. And then we have this red particle that goes in a quantum superposition of these two trajectories. And at the end, they measure a relative phase. Now, the interesting aspect of this relative phase is that this measures the gravitational phase shift of the tungsten mass. So they did it so well that basically it's as if here gravity was not acting, and here you have a gravitational field that they can feel. And this gravitational phase shift is beyond the uniform field approximation. So it is not just MGH, it has additional components in the additional terms in the Taylor expansion of the Newton potential. While the Earth doesn't matter in this description. So, this is, they call this the gravitational Aharonov-Bohm regime, the experiment. And now, what we asked with them was, okay, let us take everything that we know from current experiments. So what do we know? We know that the localized mass as light as 90 milligrams sources a gravitational field. So clearly the tungsten sources a gravitational field, and they even measured that. And then we know that the equivalence principle is valid up to experimental resolution, which is pretty good. Then we know that there are gravitational waves, and these have also been measured. Then we know that, and they measured in this experiment, that there is a gravitational phase shift between different paths. And finally, this experiment is actually a very good, an excellent test that classical gravity, which is given by the tungsten mass, and quantum theory, which is given by the behavior of atoms in the interferometer, are perfectly compatible even beyond the linear regime. And this was a regime that was not addressed before by experiments. So, okay, still classical gravity. What are we missing in order to have a superposition of gravitational fields? So what we did was to come up with a set of assumptions that have yet to be tested in experiments that would lead us to concluding that the gravitational field can be in a quantum superposition. And let me just focus, so there are, not all of them are necessary. Let me just focus on 1 and 3. The first one is the existence of a gravitational field that tells us that any massive particle that is well localized at a position x0 sources a gravitational field G with functional form x minus x0. So what we are saying here is that there is a gravitational field, full gravitational field associated to each localized particle. I'm not saying anything about delocalized particles. I don't want to make statements on that. And the third one is the quantum relativity principle that tells me that the laws of physics take the same form in every reference frame, including the reference frames associated with quantum particles, which are quantum reference frames. And then, under these two assumptions, we can map this description of the experiment into this description of the experiment, where the atom is in a fixed trajectory, and it's the tungsten that is in a quantum superposition of two different positions, and hence sources a gravitational field. Clearly, this doesn't prove the gravity is quantum. This has to be proved, but I think that it is helpful to reason in these terms because it provides a more general principle for physics that can help us to build our intuition and the framework to formulate physics when we do not have a classical notion of space-time. So to wrap up, this regime and this type of thought experiments and quantum reference frames are helpful for me from an experimental perspective because we do not know which observation would prove in a compelling way that gravity has quantum features. From a theoretical perspective, general relativity and quantum theory stand on very different conceptual frameworks, and we do not know how to reconcile them. And in this regime, we can solve open questions that will help us to make progress towards combining quantum theory and general relativity. And with this, I would like to thank you for your attention, and I'm happy to take questions.
Okay, thank you, Flaminia, for the very nice talk. I actually have a question on the concept of gravitational superposition. I mean, thinking on GR, classical GR, if I have some metric that satisfies Einstein's equation, and then I have another metric that satisfies Einstein's equation.
Right.
I cannot assure that if I add them up, then I have another metric that satisfies Einstein's equation. I mean, so how can I talk about superposition in these terms? How can I add to things if Einstein's equation are nonlinear? I mean, or can I do only the weak field limits for things are linear?
So I would say that this is mostly an open question. We know that there are regimes in which you can do it. For instance, we know that in the weak field limit you can do it because then you linearize the Einstein's equations and then it's analogous to the electromagnetic field. And you can even formulate it. And we have a paper where we calculated the quantum state of the gravitational field for a mass in a quantum superposition. So in this case, you can do it. Then, if you take a quantum information perspective, you can abstract from the specific physical configuration, and you can see, okay, which are the fundamental principles that allow me to make this statement, and then you can formulate it in abstract terms. This doesn't mean that you're identifying a physical regime in which this happens. This is yet to be done, but at least it tells you what you need in order to be able to do that.
Okay, so anyone has any questions? So we got plenty of time.
I do.
Go ahead.
I don't know. I don't know if it's actually a question or simply a thing that I don't understand. But how do you define observables in this theory? I mean, the way I think observables in classical physics, I think about them as associated with some symmetry, like killing vectors. How can I do these sort of things here?
Okay, so let me just answer in the Galilean limit, because this is the one that you can control the best.
Perfect. Yeah.
So in this case, you actually have a meaningful notion of observables. So the formalism that I showed here can actually be rephrased in terms of, okay, so you can consider n particles, which are like n particles just described normally, and then you want to get rid, with the symmetry principle, of the center of mass degree of freedom. You only want to describe relational quantities. So the way you can do that is to use constraint systems. So you impose that the total momentum is 0, and this induces a gauge symmetry on the full system. And then you want to reduce. For whom what?
For whom the momentum is 0. Okay,
so my interpretation is that this is a perspective neutral approach, and so it's nobody's perspective. So it's just a trick, it's just a mathematical trick to reduce to one specific perspective. And actually this works also with just classical reference frames. We don't need to have quantum reference frames. So classically, what you do is you break the gauge freedom, so you choose a gauge by, for instance, setting the origin at the location of a particle. In the quantum case, it is a little bit more complicated. So you project over the classical gauge condition. If you're familiar with the Page and Wooter's approach, it's a very similar technique to what you would do there. You just apply a unitary transformation and then project on the classical gauge condition. And then what I think is operationally meaningful is just a reduced one. And so the transformation that maps from one part, say you do it with respect to particle 1, you do it with respect to particle 3, and then you change from 1 to 3. And the transformation that maps one to the other is exactly the transformation that I wrote on the slide. Now, you can also define observables, and it turns out that all the observables that we have, so like X, the position of B, the position of A, PB, PA, these are exactly the Dirac observables that are the gauge invariant observables. So that's a way, so that's a way in which you can define them.
Okay. This holds for this regime of weak gravitational field that you are talking about. Okay. Thank you. Amazing talk. I'm starting understanding these things.
Thanks a lot.
So many more questions. Well, if not, I would like to thank you again, Flaminia. It was really an amazing talk, and like Luca said,
thank you very much.
We have also to try to understand this better. So it was a really good talk. Thank you for accepting the invitation.
Just write to me if you have more questions. I'm happy to answer.
Sure, I will. Well, thank you, everyone.
Thank you very much.
Thank you. Bye.